Hello everybody, my name is Daniel Mangastav, and today I'll be presenting Lab 4, Two-Dimensional Spring Mass Motion. In this lab, I use tracker video analysis and a VPython computational model to study the motion of a mass attached to a spring. My goal was to compare the experimental motion with the stimulated motion and evaluate how accurately the model represents the new system. In this slide, we have our purpose, which was to collect experimental motion using tracker, build a computational model, compare model and experiment, and verify the principle of conservation of energy. For our experimental setup and to collect the experimental data, a video of the oscillating spring mass system was analyzed using tracker. A collaboration stick with a known length of 0.7 meters was used so the software could convert pixels into real-world distances. After collaborating the video, I manually tracked the center of mass frame by frame. Tracker then generated the X and Y position data that was later imported into the VPython simulation. For our computational physics model, it was based on Newton's second law, which states that the net force acting on an object equals its mass times its acceleration. As you can see, the second formula. The two masses acting on the mass are the spring force and the gravity. The spring force follows Hooke's law and allows X to restore the spring to its relaxed length, while gravity provides a constant downward force, as you can also see from the first and the third formula. The model also calculates kinetic energy, gravitational potential energy, and spring potential energy throughout the simulation. Using the measured values for the mass, spring constant, gravity, and relaxed spring length, the program predicts the motion of the mass over time. And as you can see here, we have the given, the known value for the mass, gravity, spring constant, and relaxed spring length. Computational simulation. After importing the tracker data, the VPython program simulated the motion using numerical integration. The blue object represents the computational prediction, while the red object represents the experimental tracker data. At each small time step, the program calculates the force, updates the acceleration, velocity, and position, and then compares the predicted motion with the measured motion from the experiment. As you can see in this image, it's not currently in motion, as I only have the last captured spring screenshot, but the red dot is supposed to represent the moving data, in which at this moment is at its final resting moment. Energy analysis. This slide is meant to summarize how energy changes throughout the motion of the spring mass system. During the oscillation, energy is constantly being transferred between kinetic energy, gravitational potential energy, and spring potential energy. For example, when the mass is moving its fastest, the kinetic energy is at its greatest because velocity has the biggest effect on kinetic energy. As the mass moves higher or stretches the spring, some of that kinetic energy is converted into gravitational or spring potential energy. This transfer continues throughout the entire motion. Even though the individual forms of energy are always increasing and decreasing, the total energy remains approximately constant. This demonstrates the law of conservation of energy and confirms that computational model is accurately representing the physical behavior of the system. Position comparison. On the right, we have the energy versus time graph, and on the left, I know it might be kind of hard to see, but the top left graph is the X position versus time, and the bottom left graph is the Y position versus time. By looking at the comparison, the model follows the same overall oscillating motion as the experimental data. The peaks, valleys, and general pattern of the motion are very similar, showing that the simulation captures the behavior of the real system quite well. There are still some small differences between the two, which is expected in any experiment. These differences can result from small errors while manually tracking the mass, slight collaboration inaccuracies, or the fact that the computational model assumes ideal conditions, such as no air resistance and a perfectly elastic spring. Even with these differences, the agreement between the experimental data and the simulation shows that the mathematical model provides a reliable representation of the spring mass system. To follow up on what I said, Some potential sources of error can be manual tracking uncertainty, the camera resolution, the uncertainty in collaboration, the ignorance of error resistance, the ideal spring assumption, and numerical approximation.